Hello again, and welcome back to the Limitless Void channel. If you've made it here, perhaps the night is quiet around you. Perhaps your body is ready to rest, but your mind is still reaching for something. Something wide. Something slow and full of wonder. Tonight we return to the galaxy we call home. The Milky Way. A spiral of more than 100 billion stars turning slowly in the dark for over 13 billion years. In our last journey together, we drifted through 100 quiet truths about this galaxy. Tonight, we go further. There are more secrets held in the arms of this great spiral, more mysteries buried in its halo, more stories written in the light of ancient suns. You have nothing to do tonight but rest. Let your breath slow. Let your thoughts soften like the edge of a flame settling into embers. The galaxy will do the moving. You only need to listen. And before we begin, if these slow cosmic journeys help you find peace at the end of a long day, consider liking and subscribing to the channel. It helps others find their way here too. One quiet soul at a time. Now, let us begin. The Milky Way was not born all at once. We sometimes imagine galaxies as things that simply appeared, vast and complete, spinning from the first moments of the universe. But the Milky Way grew slowly. It assembled itself over billions of years from collapsing clouds of gas, from the debris of smaller proto-galaxies, from threads of dark matter pulling matter inward across cosmic time. It was not a single event, but a long, quiet accumulation, a gathering. The way a river is made not from one drop, but from the slow meeting of countless streams, each one finding its way downward through stone and time, joining something larger than itself. The galaxy is the sum of everything that fell toward its center, and everything that stayed. The Milky Way formed from the inside out. The oldest stars and structures in our galaxy are concentrated near its center. The halo and the thick disk came first, assembled when the universe was still young and turbulent. The thin disk, the broad flat structure where our sun lives, formed later as gas settled and cooled, spinning down into a flattened plane over billions of years. This inside-out formation means that when we look toward the galactic center, we are looking backward in time. The stars there are older, more metal-poor, born in an earlier and wilder era. The outer disk where we reside is younger, richer in heavy elements, and still forming stars today. We live in one of the galaxy's newer neighborhoods built long after the foundations were laid. The Milky Way has a bar of stars at its center. Running through the heart of the galaxy like the handle of a great cosmic pinwheel is a dense, elongated structure called the central bar. It stretches roughly 27,000 light-years from end to end, a river of stars hundreds of millions strong, rotating slowly around the galactic core. This bar is not simply decorative. It channels gas from the outer regions inward, funneling material toward the core and influencing where new stars are born. It also connects to the spiral arms, which trail outward from its ends like ribbons caught in a slow wind. The bar is one of the Milky Way's defining features, and yet for most of human history, we had no idea it was there. Hidden behind dust and distance, it was only confirmed in the last few decades. The galaxy's bar rotates at a different speed than the disk. Not everything in the Milky Way moves at the same pace. The central bar rotates with its own rhythm, separate from the overall spin of the disk. This difference in speed creates resonance points, special zones where the bar's gravitational influence meets the orbital motion of stars and gas in ways that can trigger bursts of star formation or reshape the structure of the inner galaxy. These resonances are like the harmonics of a slow galactic instrument, invisible waves shaping what grows and where. Astronomers are still mapping their effects, still learning how the bar conducts the inner galaxy's quiet symphony. It is one of the many ways the Milky Way is far more intricate than it first appears. A structure within structures. A rhythm within rhythms. The Milky Way's spiral arms are named. Among the great curving arms that trail outward from the galactic bar, astronomers have given names to the most prominent. There is the Perseus arm, sweeping outward in the direction of that constellation. The Scutum Centaurus arm, one of the two major arms in our galaxy. The Norma arm. And the Sagittarius arm, just inward of our own position. Our sun resides in a smaller partial arm called the Orion arm, sometimes called the Orion Spur. It is a minor branch connecting two of the larger arms, a quiet offshoot rather than a grand spiral. We are not in the most prominent part of our galaxy. We are in a kind of alley between the main thoroughfares, orbiting at an unremarkable distance, in an unremarkable location, around a perfectly ordinary star. And somehow, from this ordinary vantage point, we have managed to deduce the shape of the extraordinary place we live in. The galaxy has more than one population of stars. Astronomers have long recognized that the Milky Way's stars can be divided into distinct populations based on their age, composition, and location. Population 1 stars are younger, metal-rich, and found mostly in the spiral arms and the thin disk. Our Sun belongs to this group. Population 2 stars are older, metal-poor, and scattered through the halo and the thick disk. They formed in an earlier era when the universe had fewer heavy elements to offer. And some researchers speak of population 3 stars, the hypothetical first generation of stars ever born, formed from pure hydrogen and helium in the universe's first few 100 million years. None have been confirmed yet, but their fingerprints may linger in the compositions of the oldest stars we can find. The galaxy's magnetic field runs along its spiral arms. Threading through the Milky Way, invisible and immense, is a magnetic field. It flows along the spiral arms like a river inside a river, guiding the motion of charged particles, shaping the structure of gas clouds, and influencing where new stars can form. This field is weak by the standards of ordinary magnets, but it spans the full breadth of the galaxy. Across thousands of light years, it holds a quiet coherence, a direction, a tendency. How this field was generated and how it sustains itself over billions of years is still an open question. Some models suggest it is maintained by the motions of electrically charged gas, a kind of galactic dynamo spinning deep within the disk. The Milky Way hums with magnetism we cannot feel and can barely measure, but it is there, shaping everything. Pulsars are the galaxy's most precise timekeepers. When a massive star exhausts its fuel and collapses, what remains is sometimes a neutron star. A city-sized object so dense that a teaspoon of its material would weigh billions of tons. Some of these neutron stars spin rapidly, emitting beams of radio waves that sweep through space like lighthouse beams. These are pulsars, and some of them rotate hundreds of times per second with such mechanical precision that they rival atomic clocks. The Milky Way contains thousands of known pulsars scattered through the disk and halo. They tick away in the dark, indifferent to time, beaming their signals outward. Astronomers use them to probe the density of space between the stars, to test theories of gravity, and to listen for gravitational waves. They are the galaxy's heartbeats, rapid, steady, and ancient. There are neutron stars so magnetic they defy imagination. Beyond ordinary pulsars lies an even stranger class of neutron star called the magnetar. These objects possess magnetic fields trillions of times. stronger than Earth's. So powerful that from across a galaxy, a magnetar flare could strip electrons from atoms in its path. On December 27, 2004, a magnetar in our own galaxy released a burst of energy in a fraction of a second that briefly outshone everything else in the sky. It struck Earth's upper atmosphere from 50,000 light years away and was still powerful enough to disrupt radio communications from halfway across the Milky Way. A fraction of a second, and the whole galaxy shuddered with it. These objects remind us that the universe contains forces so extreme they strain the very language we use to describe them. White dwarfs will outlive almost everything. When a star like our Sun reaches the end of its life, it will shed its outer layers in a luminous nebula, leaving behind its dense core. A white dwarf. This object, no larger than Earth but containing most of the original star's mass, will cool slowly over trillions of years. There's no fuel left to burn, no fusion to sustain it. It simply radiates the heat it has stored. The Milky Way is full of white dwarfs, billions of them scattered through the disk and halo, glowing faintly in the dark. The youngest are still hot and blue-white. The oldest have cooled to dim orange or red. Eventually, in timescales the universe has not yet reached, they will cool completely into black dwarfs. Dark, cold, inert, patient beyond any measure we have words for. The galaxy contains stellar black holes by the millions. Not all black holes are supermassive. Scattered through the Milky Way are the remnants of massive stars that collapsed at the end of their lives. These stellar black holes range from a few times the mass of the Sun to perhaps dozens of times more. They are invisible individually, betraying their presence only by their effect on nearby gas or companion stars. Astronomers estimate there may be tens of millions of stellar black holes in the Milky Way alone, most of them drifting silently, undetected, through the disk. They are the endpoints of the most massive stars, the final chapters of the brightest lives. The galaxy is threaded with these quiet singularities, points where our physics runs out of language, scattered across the arms and the core like dark seeds in an ancient field. Intermediate mass black holes may be hiding in globular clusters. Between stellar black holes and the supermassive monster at the galaxy's center lies a gap. Are there black holes of intermediate mass, thousands or millions of times the mass of the Sun, somewhere in between? The answer may lie in globular clusters. These dense, ancient spheres of stars orbiting the galaxy's halo could harbor intermediate black holes at their cores. Evidence is tantalizing but not yet conclusive. Some clusters show gravitational dynamics that hint at a hidden central mass. Others appear empty. The search continues, careful and slow, across hundreds of clusters scattered across the halo. If intermediate black holes exist in these ancient clusters, they may be the seeds from which supermassive black holes like Sagittarius A star grew. The missing link in the story of cosmic darkness. The galaxy's disk is thicker in some places than others. The thin disk of the Milky Way is not uniformly flat. It varies in thickness across its breadth, becoming thicker toward the inner galaxy where stars are more numerous and gravitational interactions more frequent. Near our own position, the disk spans perhaps 1,000 to 1,500 light years from top to bottom. But toward the center, it puffs outward further still. There is also the thick disk, a distinct structural component containing older stars with higher random velocities. It extends further above and below the galactic plane than the thin disk, like a soft blur surrounding a sharp line. The galaxy is layered in ways we are still learning to read. Each layer carries its own population of stars, its own history, its own rhythm of motion. Nebulae are the galaxy's most visible nurseries. Among the most beautiful objects in the galaxy are nebulae. These vast clouds of glowing gas, sculpted by the light and winds of nearby stars, take forms that seem too elaborate to be real. The Orion Nebula, the Eagle Nebula with its towering pillars of creation, the Carina Nebula with its chaotic churning of hot gas and newly born stars. These structures are the birthplaces of new suns and, in time, new worlds. They glow because ultraviolet radiation from young stars inside them strips electrons from hydrogen atoms. And when those electrons recombine, they release light. The nebulae shine not with reflected light, but with their own, energized from within. They are lit from the inside by the very process of creation. The Milky Way is still chemically evolving. Every generation of stars changes the chemical composition of the galaxy. As stars burn and die and scatter their material back into space, the interstellar medium grows richer in heavy elements. Oxygen, carbon, silicon, iron? These elements build up slowly across billions of years. The galaxy today is far more chemically complex than it was when it first formed. Young stars forming now have access to a richer palette of elements than the ancient halo stars born near the beginning. This chemical evolution is ongoing. The Milky Way is not a static chemical environment. It is a place where each generation of stars inherits a slightly more complex universe than the one before it. In this way, the galaxy grows more intricate with time, slowly enriching itself across eons. Not all star formation is the same. Stars form across a wide range of masses, from tiny red dwarfs barely large enough to sustain fusion, to brilliant blue giants 100 times the mass of the Sun. The distribution of these masses is not random. It follows a pattern called the initial mass function, a statistical fingerprint of how star formation works. Small stars are far more common than large ones. For every massive blue giant born in a stellar nursery, many dozens of dim red dwarfs emerge alongside it. This matters because small stars live for tens or even hundreds of billions of years, while massive stars burn through their fuel in mere millions. The Milky Way's stellar population is dominated by these small, slow-burning stars, patient, dim, and enormously long-lived. Red dwarfs may be the most common hosts of planets in the galaxy. Because they are so numerous, red dwarf stars are the most common type in the Milky Way by a wide margin. And recent observations have shown that many of them host planetary systems, worlds orbiting close to their dim stars, sometimes in the habitable zone where liquid water could exist. These planets are very different from Earth in many ways. Tidally locked, bathed in flares, orbiting in the warmth of a feeble sun. But the sheer number of red dwarfs makes them statistically dominant in the count of potentially habitable worlds across the galaxy. If life can find a foothold around these small, ancient stars, then the galaxy may be far more populated than we have dared to imagine. The Milky Way's oldest stars offer a window into the early universe. Among the most remarkable tools available to astronomers are the ancient metal-poor stars drifting through the Milky Way's halo. These stars, some nearly as old as the universe itself, carry in their atmospheres a chemical record of the conditions present when they formed. By analyzing the precise abundances of different elements in their light, astronomers can reconstruct what the early universe looked like before the first generation of stars had lived and died. They are living artifacts. They have been burning quietly for 13 billion years, waiting for us to develop the instruments sensitive enough to read their story. And when we do, we find ourselves looking not at a star, but at a message. A letter written in light, sealed in the heart of a sun, waiting to be read across the length of all of human history. Globular clusters hold some of the galaxy's most ancient stars. We have spoken before of globular clusters, those great spherical gatherings of hundreds of thousands of stars orbiting the Milky Way in the halo like ancient satellites, but it is worth dwelling on their age. Some globular clusters contain stars more than 12 billion years old, formed before the Milky Way's disk had even settled into its current shape. These clusters are so old that astronomers have used them to constrain the age of the universe itself. If the universe were younger than its oldest clusters, something would be wrong. They serve as cosmic calibration points. Their age tells us how long the universe has been making stars, and by extension, how long it has been at all. They are the galaxy's elders, quiet, dense, and unimaginably patient. Some globular clusters may be the remnant cores of swallowed galaxies. When smaller galaxies fall into the Milky Way and are torn apart, their stars scatter into streams and shells. But in some cases, the dense nucleus of the smaller galaxy may survive, stripped of its outer layers but still intact at its core. Some astronomers believe that the globular cluster Omega Centauri, the largest in the Milky Way, may be exactly this: a surviving core from a dwarf galaxy consumed long ago. It contains multiple stellar populations, different ages and compositions mixed together, which is unusual for a typical cluster. That diversity may be the fingerprint of a galaxy that once had the time to form several generations of stars before being devoured. Omega Centauri drifts in the halo now, ancient and vast, carrying the memory of a world that no longer exists. The halo of the Milky Way extends far beyond what we can see. When we picture the Milky Way, we tend to picture the disk, the flat, luminous spiral with its trailing arms and glowing core. But surrounding that disk in all directions is the halo, a great spherical region extending hundreds of thousands of light years from the center. It contains ancient stars, globular clusters, and vast quantities of dark matter. The halo is not empty. It is permeated by hot gas, streams of stars from ancient mergers, and the invisible scaffolding of dark matter that gives the Milky Way much of its gravitational mass. If we could see the halo glowing all at once, the galaxy would appear not as a flat disk, but as a diffuse glowing sphere with the bright disk merely its central plane. The halo is most of the galaxy. We just cannot see it. The galaxy breathes in gas from the cosmic web. Surrounding all galaxies, connecting them in vast filaments across the universe, is the cosmic web, a network of dark matter and gas stretching across billions of light years. The Milky Way is embedded in this web, and from it, it slowly draws in gas, cool streams of hydrogen and helium flowing inward along filaments, replenishing the raw material from which stars are made. This inflow is quiet, gradual, and ongoing. Without it, the galaxy might have exhausted its star-forming gas billions of years ago. The cosmic web feeds the Milky Way the way rain feeds a river. Slowly from great distances, from sources invisible to the naked eye, the galaxy is not closed. It is connected to the universe, embedded in something far larger, breathing in from the vast dark between the galaxies. The Milky Way also expels gas. The galaxy does not only take in, it also exhales. Supernovae and the intense radiation of massive stars drive powerful winds outward from the disk, launching hot gas into the halo and beyond. These galactic winds carry with them enriched material, elements forged in stellar cores and scattered in stellar depths. Some of this gas escapes the galaxy entirely, drifting into the intergalactic medium. Some falls back in what astronomers call the galactic fountain, raining back down onto the disk after cooling in the halo. The galaxy cycles its material through this fountain over and over. A long, slow breath inward, a long, slow breath outward, maintaining a balance between the gas it has and the stars it makes. There's a vast reservoir of hot gas surrounding the Milky Way. Beyond the visible disk, but still within the gravitational reach of the galaxy, observations have revealed an enormous corona of hot, diffuse gas, extending hundreds of thousands of light years in all directions. This hot, gaseous halo is faint and difficult to detect, but its total mass may rival the visible mass of the entire galaxy. It glows in X-rays, too faint for the naked eye but detectable with space telescopes tuned to high-energy light. This corona is a reservoir, a storehouse, of material that has been ejected from the disk over billions of years. It is the galaxy's atmosphere, vast, hot, and invisible, wrapping the entire system in a cocoon of diffuse warmth that stretches nearly to the edge of what we can call our own. The Magellanic Clouds are leaving a trail of stars. High in the southern sky, the large and small Magellanic Clouds are visible to the naked eye from the southern hemisphere. Two irregular satellite galaxies of the Milky Way, glowing like detached fragments of our own galaxy against the dark. They orbit the Milky Way in a complex, slowly decaying path, and their interaction with our galaxy is not passive. Behind them, trailing across the sky in a great arc, is the Magellanic Stream, a ribbon of gas stripped from the clouds by the tidal forces of our galaxy. This stream stretches more than halfway around the sky in total extent. It is one of the largest structures associated with the Milky Way, and it is feeding us. As the gas in the stream eventually falls into our galaxy, it adds new material for future star formation. The Magellanic Clouds will one day be consumed. The large and small Magellanic Clouds have been companions to the Milky Way for billions of years. But their orbit is not stable. Gravitational interactions are slowly tightening their path. In the distant future, billions of years from now, the Milky Way's gravity will likely shred them as it has shredded so many smaller galaxies before. Their stars will scatter into stellar streams. Their gas will flow into the disk. Their identity will dissolve into our own. It is not a violent end, at least not by cosmic standards. It is simply the nature of gravity. The strong pull the weak inward, the large consume the small. The Milky Way has done this many times before. It will do it again, and each time it grows a little larger, a little richer, a little older. The Milky Way has satellite galaxies beyond the Magellanic Clouds. More than 50 small, dwarf galaxies orbit the Milky Way, most of them too faint to see without a telescope. The Sagittarius dwarf galaxy, currently being torn apart by our gravity, stretches its stars across a vast arc around the southern sky. The Canis Major dwarf, so close that it may be merging with our disk right now. Sculptor, Fornax, Carina, Draco. Each one a small, dim collection of ancient stars in a slow gravitational embrace with our galaxy. Some of these dwarfs are among the oldest and most dark, matter-dominated objects known, containing more dark matter per visible star than almost anything else in the universe. They are the small and the quiet, living in the gravity shadow of something vast. And in that way, perhaps they are something we understand. The Milky Way's rotation tells us where the dark matter is. One of the most powerful tools for mapping dark matter in the Milky Way is the rotation curve. By measuring how fast stars orbit the center of the galaxy at different distances, astronomers can deduce how much mass is contained within each orbit. And the results tell a clear story. There is far more mass than we can see. In the outer reaches of the galaxy, stars orbit at speeds that imply the presence of enormous quantities of unseen mass surrounding and permeating the disk. This mass is the dark matter halo. By watching how the galaxy turns, we can map what we cannot see. Darkness made visible through motion, a profound and humbling technique that has revealed the true shape of our invisible home. The galaxy's total mass is uncertain. Despite decades of careful measurement, the total mass of the Milky Way remains difficult to pin down precisely. Estimates range from about 500 billion solar masses to more than a trillion. The uncertainty comes largely from the dark matter halo, which extends far beyond the disk in ways that are hard to sample directly. To measure the mass of the outer halo, astronomers track the motions of distant stars, globular clusters, and satellite galaxies, using them as probes of the gravitational field at large radii. Each new survey refines the estimate slightly. The picture is becoming clearer, but the Milky Way remains, in some fundamental sense, a place whose full dimensions we are still learning. We live inside it, and yet in many ways it remains a mystery. Galactic archaeology recovers the history of mergers. By studying the positions, velocities, ages, and chemical compositions of millions of stars, astronomers can work backward. They can identify groups of stars that share a common origin, that move together through the galaxy, that carry the same chemical fingerprints. These groups are the remnants of ancient mergers, stars from galaxies long since consumed. This practice is called galactic archaeology, and it has revealed a surprisingly rich merger history for the Milky Way. The Gaia Enceladus event, a major merger about 10 billion years ago, contributed many of the stars in the inner halo. Other named events, the Sequoia merger, the Helmi streams, represent other ancient collisions. The Milky Way is a composite object, assembled from the ruins of many smaller galaxies. Its history is written in the motion and chemistry of its stars. The galaxy experienced a period of rapid star formation early in its history. In the first few billion years of the Milky Way's existence, star formation was intense. The galaxy was rich in gas, turbulent with the energy of its assembly, and producing new stars at a rate far higher than today. This era left its mark in the form of the old, metal-poor stars in the thick disk and halo. Stars born in a time of abundance, when the galaxy was young and still hungry. That early burst of creation seeded the galaxy with the first heavy elements, enriching the interstellar medium and setting the stage for everything that followed. The Milky Way today is quieter, more settled. Its great burst of creation is long past. We live in the galaxy's middle age, still productive but no longer frantic. The galaxy likely had a more violent past. Sagittarius A star, the supermassive black hole at the center of the Milky Way, is relatively quiet today. It accretes gas only occasionally, producing brief flares before settling back into silence. But the evidence suggests it was once far more active. The Fermi bubbles, those vast lobes of high-energy gas stretching above and below the galactic center, may be relics of a period when the black hole was feeding voraciously. Perhaps millions of years ago, perhaps even more recently in cosmic terms, the galactic center blazed with the energy of an active galactic nucleus, perhaps even a quasar. Gas fell in. Energy poured out. The entire inner galaxy was flooded with radiation. We cannot see that era directly, but we can read its aftermath in the structures it left behind, ghostly and glowing in wavelengths invisible to human eyes. The galactic center is a crowded and extreme environment. The inner few hundred light years of the Milky Way are unlike anywhere else in the galaxy. Stars are packed together at densities millions of times greater than in the solar neighborhood. Giant molecular clouds fill the region with gas and dust. Magnetic fields twist and tangle. Supernova remnants collide. X-rays and infrared glow from every direction. At the very heart of this tumult sits Sagittarius A star, around which a special population of stars orbits in tight, rapid ellipses. These S stars, as they are called, move faster than any other stars known, their orbits sweeping close to the event horizon of the black hole and then swinging wide. Tracking them has allowed astronomers to measure the mass of the black hole with extraordinary precision. They are the probes we use to feel the edge of the abyss. Stars near the galactic center age differently. The intense environment of the inner galaxy affects star formation and stellar evolution in unusual ways. Stars form from gas clouds that are warmer and more turbulent than those in the outer disk. Radiation pressure from nearby massive stars in the black hole interferes with the normal collapse of gas. And yet stars do form there, including some surprisingly massive and young ones. How such young stars could have formed so close to the black hole is still debated. One possibility is that they migrated inward from further out. Another is that the gas clouds in that region are dense enough to overcome the extreme conditions and collapse on their own. The galactic center is a laboratory for stellar physics unlike any other, a place where our usual models must work harder to keep up with reality. The Milky Way has a complex history of star formation across the disk. Star formation has not proceeded evenly across the galaxy. Different regions have had their own histories, their own peaks and valleys of activity. The inner disk formed many of its stars early. The outer disk has been forming them more gradually and recently. Some regions have been quiet for billions of years. Others are active nurseries today. The result is a patchwork galaxy, with stellar populations of different ages distributed unevenly across the disk. By studying these populations, astronomers can reconstruct the star formation history of different galactic regions, building up a detailed picture of how the Milky Way assembled itself over time. It is not a uniform story. It is a mosaic. Each tile a different color, a different age, a different history. Exoplanets have been found orbiting all kinds of stars in the Milky Way. The Kepler Space Telescope and its successor, TESS, have revealed that planets are not rare. They are common. Around red dwarfs, around sun-like stars, around giant stars, around stars in binary systems. Planets of every conceivable size and orbital arrangement have been found scattered across the galaxy. Rocky worlds, gas giants, super-Earths, sub-Neptunes. Planets orbiting two stars at once in figure-8 paths that seem impossible until they are observed. The galaxy is full of worlds. Most of them we will never see directly, but their existence suggests that wherever stars form in the Milky Way, worlds follow close behind. The galaxy is not just a collection of stars, it is a collection of solar systems, each one its own story, its own experiment in chemistry and gravity. The cosmic distance ladder begins in the Milky Way. When astronomers measure distances in the universe, they rely on a series of overlapping techniques, each one building on the last like rungs on a ladder. The first rungs of that ladder are anchored here in the Milky Way. Parallax measurements for nearby stars, variable stars and globular clusters, distances to the Magellanic Clouds, each step calibrated against the last. Without these first rungs inside our own galaxy, we could not measure the distances to other galaxies. We could not know the expansion rate of the universe. We could not determine its age. The Milky Way is not just our home. It is the foundation on which all of extragalactic astronomy is built. When we measure the size of the universe, we begin by measuring our own galaxy's backyard. The galaxy vibrates with gravitational waves. In 2015, the first detection of gravitational waves was announced. Ripples in spacetime produced by the merger of two black holes more than 1 billion light-years away. Since then, dozens of mergers have been detected, including collisions of neutron stars that produce both gravitational waves and light simultaneously. These events happen throughout the universe, and the Milky Way is no exception. Merging neutron stars and black holes in our own galaxy produce gravitational waves that pass through us undetected, for now, simply because our instruments cannot yet sense the quieter, lower frequency waves produced by the slow spiraling of compact objects in the galactic disk. But a future space-based observatory may change that. And when it does, we may hear the Milky Way itself singing in gravitational wave frequencies we have never heard before. The Sun will leave the main sequence in about 5 billion years. Like all stars of its mass, the Sun is on a one-way journey. It has been burning hydrogen in its core for 4.5 billion years. In roughly 5 billion more, that hydrogen will run low. The core will contract. The outer layers will expand. The Sun will become a red giant, swelling to perhaps 100 times its current size. Mercury and Venus will almost certainly be consumed. Earth may survive, but it will be a scorched and airless rock. Eventually, the Sun will shed its outer layers in a planetary nebula, leaving behind a white dwarf at its heart. A quiet, cooling remnant of what was once the source of all light and warmth for a living world. This is not an ending to fear. It is simply the life cycle of a star, and it is one of the commonest stories the galaxy tells. The galaxy's disk contains ancient fossils of its own formation. Deep within the thick disk of the Milky Way, stars orbit with a different character than those in the thin disk. They are older, with more random motions, scattered further above and below the galactic plane. These stars are the survivors of the Milky Way's turbulent early period, when the galaxy was not yet settled, when mergers and gas infall stirred everything into a thicker, hotter disk. The thick disk preserved that turbulence in the motion of its stars. By studying these stars today, we read the conditions of the galaxy before it found its current equilibrium. They are fossils not in stone, but in stellar dynamics. Memories written in the random velocities of ancient suns, preserved for billions of years in the slow turning of the disk. The thin disk is where most star formation happens today. In contrast to the thick disk, the thin disk of the Milky Way is where the galaxy is still most actively making new stars. It is younger, flatter, and richer in the gas and dust needed for star formation. The spiral arms trace through it. The nebulae glow within it. The molecular clouds drift through it, cold and dark, waiting for the right conditions to collapse. Our solar system lives in the thin disk, orbiting at a distance of about 26,000 light-years from the galactic center. We are embedded in the galaxy's most active layer. Around us, at distances we cannot see directly, stellar nurseries are at work. New suns are igniting. New worlds are forming. The Milky Way's future is being written in the thin disk right now, in the quiet dark between the stars, where gas and gravity are negotiating the shape of things to come. The galaxy's arms trigger star formation as gas passes through them. We have spoken before of how spiral arms are not solid structures, but density waves. But it is worth lingering on what that means for life in the galaxy. As a cloud of gas enters the compression zone of a spiral arm, it is squeezed. Its density increases. Gravity gains the upper hand. collapse begins. Stars ignite along the leading edge of the arm, lighting it up with blue-white brilliance. These are the hottest and most massive stars, the ones that live for only a few million years before exploding as supernovae. By the time the gas cloud has passed through the arm and moved out the other side, it has given birth to a cluster of new stars, and those stars have already begun their brief and brilliant lives. The spiral arms are not just beautiful features of the galaxy's shape. They are engines of creation, places where the density wave compresses the galaxy's raw material and turns it into light. We orbit through these arms on our long galactic year, and each time we enter one, the region around us briefly becomes more active, more luminous, more alive. The galaxy's bulge is home to some of the oldest and densest stellar populations. At the heart of the Milky Way, surrounding the bar and the black hole, is the central bulge, a dense, roughly spheroidal region packed with stars at concentrations far exceeding those in the disk. The bulge contains both old and young stars, a mix of ancient, metal-poor populations and newer stars formed from gas funneled inward by the bar. Observing the bulge is difficult from our position in the disk because dust clouds block our view in visible light. Infrared and radio telescopes peer through the dust to reveal a complex inner world, rich in stellar variety and gravitational drama. The bulge is the oldest inhabited region of the galaxy, a dense, ancient city at the center of a sprawling, spiraling metropolis, and we live far out in its quieter suburbs. The Milky Way is not the largest galaxy in the local group. Our galaxy is impressive. More than 100 billion stars, 100,000 light-years across, a trillion solar masses of total material. But in the local group, the collection of about 80 galaxies gravitationally bound together in our cosmic neighborhood, the Milky Way is second in size. Andromeda is larger, more massive, containing more stars. It is approaching us at about 110 kilometers per second, closing the distance of more than 2 million light-years at a pace that feels slow, only because the universe operates on scales that dwarf human experience. In about 4.5 billion years, the two great spirals will meet. Neither will be destroyed, but both will be transformed. Two great galaxies merging slowly into one. The Milky Way and Andromeda are falling toward each other because of the local group's gravity. The approaching collision with Andromeda is not simply the result of Andromeda's individual motion. It is driven by the overall gravitational dynamics of the local group. The two largest galaxies in the group are the dominant gravitational attractors. Everything else orbits around, and between, and within their mutual influence. The smaller galaxies of the local group, the Triangulum Galaxy, the Magellanic Clouds, the dozens of dwarf galaxies, are all embedded in this gravitational dance. And slowly, over the coming billions of years, the local group will collapse inward on itself. The galaxies will merge into one another. The local group will become a single large elliptical galaxy, floating alone in an expanding universe where all other galaxy groups have already receded beyond the horizon of visibility. Cosmic expansion is pulling distant galaxies away from us. On the largest scales, the universe is expanding. Galaxies beyond the local group are not simply moving through space. Space itself is stretching between us and them. The further away a galaxy is, the faster it appears to recede. Some galaxies are receding so fast that their light will never reach us. They have crossed the cosmic horizon. Our observable universe is already finite, bounded not by a wall, but by the distance light has had time to travel since the Big Bang, and by the ever-accelerating expansion that pushes distant objects beyond our reach. The Milky Way is embedded in a universe that is, in the long run, becoming lonelier. The local group will persist. But the vast web of galaxies we can now observe will slowly, over trillions of years, vanish into the dark. There are likely billions of rogue planets drifting between the stars. Planets do not always stay with their parent stars. Gravitational interactions during the formation of a solar system can eject planets outward, sending them drifting through the galaxy without a sun to orbit. These rogue planets float in the dark between the stars, cold, sunless, and alone. Astronomers have begun to detect them, not by their light, but by the way their gravity briefly bends and amplifies the light of background stars as they pass in front of them. Early estimates suggest that rogue planets may outnumber stars in the galaxy. Billions of silent worlds drifting through the dark in utter cold, carrying within them the frozen record of solar systems that once held them and then let them go. The interstellar medium contains molecules essential for life. The space between the stars is not empty. It is filled with gas and dust, and within that gas, astronomers have detected hundreds of different molecules. Water, ammonia, methane, carbon monoxide, and more complex organic molecules, including amino acids and some meteorites that carry interstellar material. The building blocks of life appear to form naturally in the cold, dense regions of space. The chemistry of life may be universal, seeded through the galaxy by the natural processes of star formation and stellar death. Every nebula, every molecular cloud, every drifting comet is a chemical factory operating at temperatures near absolute zero, producing molecules that, given the right conditions, can become the precursors of biology. The Milky Way is not a sterile place. It is a place rich in the raw materials of life. The galaxy has regions of low and high star formation. Not all parts of the Milky Way are equally active. The inner regions, closer to the galactic center, have experienced more star formation historically and still contain dense gas available for new stars. The outer disk is less dense, more quiet. But even in the outer galaxy, star formation continues in pockets of cool gas where density is sufficient for collapse. Some regions of the galaxy are star formation deserts, wide stretches of relatively low density gas where stars form rarely, if ever. Other regions are vibrant stellar nurseries, producing dozens or hundreds of new stars in tight clusters within giant molecular clouds. The distribution of star formation across the Milky Way is not uniform. It is a patchy, irregular landscape of activity and quiet, shaped by gravity, gas density, and the lingering effects of ancient events. Infrared astronomy has transformed our understanding of the galaxy. For most of human history, our view of the Milky Way was limited to visible light. And visible light is blocked by the dust clouds that fill much of the galactic disk. Infrared radiation, with its longer wavelengths, passes through dust more easily. When infrared telescopes were developed and eventually placed in space, they revealed a galaxy invisible to the naked eye. Stellar nurseries glowing behind their dusty veils, the warm dust lanes of the spiral arms, the dense core of the galaxy burning in infrared brilliance. The Spitzer Space Telescope, the Herschel Observatory, and the James Webb Space Telescope have each extended our infrared vision further, peeling back the dust curtain to show us a galaxy we could not see before. Infrared astronomy did not just change what we knew, it changed what we could know. The James Webb Space Telescope is revealing new details of the galactic ecosystem. With its extraordinary sensitivity to infrared light, the James Webb Space Telescope has already produced images of regions in and around the Milky Way of breathtaking detail. Star-forming regions like the Carina Nebula have been resolved at scales never before possible, revealing the intricate structures of gas and dust, the pillars and sheets and voids shaped by the radiation and winds of newborn stars. Webb is also probing the atmospheres of exoplanets orbiting stars within the galaxy, searching for chemical signatures that might hint at the presence of biology. It is the most powerful astronomical tool humans have ever built. And it is pointed, among other places, at the galaxy we live in, helping us understand a home we thought we knew, and finding in it depth we had not imagined. Radio astronomy has mapped the cold gas of the galaxy. Stars are made of gas, and the most abundant gas in the galaxy is cold, neutral hydrogen. This hydrogen does not emit visible light, but it does emit a characteristic radio signal at a wavelength of 21 centimeters. By mapping this radio emission across the sky, astronomers have traced the distribution of hydrogen gas throughout the Milky Way. This 21-centimeter map has been one of the most important tools for understanding the galaxy's large-scale structure. It revealed the spiral arms before optical observations could confirm them. It showed the warp of the disk. It traced the extent of the gas beyond the visible stars. Radio astronomy gave us a view of the cold skeleton of the galaxy, the raw material from which everything visible was built. The Milky Way contains both open and globular star clusters. We have spoken of globular clusters, those ancient compact spheres in the halo. But the galaxy also contains open clusters, much younger and looser groupings found mainly in the disk. The Pleiades, visible to the naked eye in the constellation Taurus, is one. A cluster of young blue stars born together from the same cloud only about 100 million years ago. Open clusters are not held together as tightly as globular clusters. Over time, the gravitational tides of the galaxy pull them apart, scattering their stars into the general stellar field. The Pleiades will eventually disperse. Its stars will drift apart and lose their common identity. For now, they travel together, young and luminous, a brief gathering of stars that will slowly loosen its grip on itself across the coming hundreds of millions of years. Variable stars pulse to mark time and distance. Cepheid variable stars, those pulsating giants whose brightness oscillates with clock-like regularity, were the key that unlocked the scale of the universe. In the 1920s, Edwin Hubble used Cepheids in the Andromeda Galaxy to prove that it lay far beyond the Milky Way, settling a long debate and expanding humanity's conception of the cosmos overnight. Today, Cepheids and other variable stars remain essential tools for measuring distances across the Milky Way and beyond. They pulse in the dark like lighthouses with known candle power, their distance calculable from the simple relationship between their period and their luminosity. They were the rulers with which we measured the galaxy, and they remain among the most reliable tools we have for placing ourselves in the vast structure of the universe. The Milky Way contains regions where gravity distorts space-time measurably. Gravity, as Einstein described, curves space-time. And the galaxy contains regions where that curvature is extreme enough to produce observable effects. Near the supermassive black hole, space-time is so severely warped that light bends, time dilates, and the ordinary rules of orbital motion break down. But even elsewhere in the galaxy, subtler effects accumulate. Gravitational lensing, the bending of light from distant stars by intervening mass, reveals itself in the brightening of background stars as a foreground object. Perhaps a star or a small black hole passes in front. These micro-lensing events have been used to probe the distribution of mass across the disk and halo, to search for dark objects that would otherwise be invisible. The galaxy is a lens as well as a light source. It bends the universe around itself. The Milky Way's future in 5 billion years will look very different. We have spoken of the Sun's fate and the Andromeda merger. But 5 billion years from now, the entire galactic landscape will be transformed. The Sun will be in its red giant phase. The thin disk will still be forming stars, though at a lower rate. The Magellanic Clouds will have been more thoroughly disrupted. The inner galaxy will be older and quieter. And Andromeda will be close. Not yet colliding, but close enough that its gravity will have begun to distort the outer disk of the Milky Way. The night sky from a world orbiting a sun in that era would look profoundly different from what we see tonight. Streams of stars from ancient mergers spreading across the sky? The great oval glow of Andromeda swelling slowly larger from decade to decade. The galaxy as we know it is a snapshot, a moment in a much longer story. The Milky Way will eventually settle into an elliptical galaxy. When the Andromeda merger is complete, perhaps 6 or 7 billion years from now, the combined system will not look like either of its progenitors. The spiral structure will be lost. The disk will have been disrupted beyond recovery. The stars from both galaxies will have settled into a large, featureless elliptical galaxy. Elliptical galaxies are the quietest type. They have exhausted most of their gas and they form few, if any, new stars. They glow with the soft red and orange light of aging stars. They rotate without distinct structure, a smooth sphere of stellar fire slowly cooling over trillions of years. The galaxy we call home will one day become one of these gentle spheres. All memory of its spiral arms erased. All traces of its current identity dissolved into something older and quieter. In the far future, the stars will die one by one, zooming out even further across timescales almost incomprehensible. The galaxy's story ends with darkness. The massive stars will die quickly. The sun-like stars within 10 or 20 billion years. The red dwarfs will burn for trillions, but eventually the last star in the Milky Way will exhaust its fuel and fade. Black holes will remain for far longer, slowly evaporating through a process called Hawking radiation over timescales so vast that the current age of the universe is negligible by comparison. And after that, on timescales beyond any number that carries ordinary meaning, even the black holes will be gone. The galaxy will be dark, cold, still. A silence where 100 billion suns once burned. But that is an unimaginably long way off. Tonight, the galaxy still turns. Stars still ignite in molecular clouds. A pulsar somewhere in the disk still ticks out its patient rhythm. A white dwarf in the halo still glows faintly with stored heat. And somewhere in the Orion Spur, on a small rocky planet orbiting an unremarkable star, a living being is lying down to sleep, listening to the slow story of the galaxy they live in. The galaxy carries the history of the universe in its stars. When we look at the Milky Way's oldest stars, we are looking at survivors. Objects that have persisted through more than 13 billion years of cosmic change. They have orbited the galaxy dozens of times. They have watched the universe cool and expand around them. They have outlasted the galaxies that formed alongside them in the early universe. These ancient stars are not simply old. They are archives. Each one encodes in its chemistry and its motion a piece of the history of how the universe came to be what it is. By reading them carefully, we read the past. By understanding the past, we begin to understand what is happening now and what is yet to come. The galaxy is a library. Its books written not in ink but in the light of ancient suns. The Milky Way is one of many. In the observable universe, there are estimated to be more than 2 trillion galaxies. 2 trillion. Each one a system of billions or hundreds of billions of stars. Each one a galaxy in its own right, with its own history of mergers and star formation, its own central black hole, its own dark matter halo, its own spiraling arms or smooth elliptical form. The Milky Way is just one of these. One galaxy among 2 trillion, and yet it is the one we know, the one we live inside, the one whose light we have been mapping for centuries, whose structure we have been piecing together observation by careful observation. It is ordinary in the grandest possible sense, and it is ours. And that makes it the most extraordinary object in the universe, simply because we are here to wonder at it. The galaxy is a place where physics becomes personal. Dark matter, quantum mechanics, general relativity, stellar nucleosynthesis, these are not abstract subjects when we understand that we live inside their effects. The iron in your blood was forged in the heart of a dying star. The calcium in your bones was scattered by a supernova explosion billions of years before the sun existed. The oxygen you are breathing right now was synthesized in stellar interiors and released into the interstellar medium long before the solar system formed. You are not a visitor to the galaxy. You are made of it. Every atom of your body traces its origin back through the galaxy's history to a star, to a supernova, to the earliest epochs of cosmic time. You are the galaxy in one of the forms it has learned to take. Everything we see at night is part of the same structure we live in. When you look up on a clear night and see the stars, you are looking at the Milky Way from the inside. Those stars are not in some other place. They are your neighbors. Separated by light years, yes, but part of the same rotating disk, the same gravitational system, the same slow galactic orbit around the same center. The faint band of the Milky Way itself, visible from dark skies as a river of light across the sky, is the compressed glow of billions of stars in the disk, seen edge on from our position within it. You are looking through the galaxy at itself. You are inside the picture, and somehow knowing that does not make the view smaller. It makes it larger, more intimate, more astonishing. The search for life in the galaxy is one of the great open questions of science. With so many stars, so many planets, so many molecular clouds seeded with the building blocks of biology, the question of whether life exists elsewhere in the Milky Way is not a fringe concern. It is one of the most serious and actively pursued questions in science. The search for extraterrestrial intelligence, the study of exoplanet atmospheres for biosignatures, the exploration of Mars and the icy moons of Jupiter and Saturn, all of these are attempts to find whether biology is a local accident or a universal feature of a galaxy rich in chemistry and energy and time. We do not yet know the answer, but the galaxy is old enough and large enough that if life arises wherever conditions allow, it has had billions of years and hundreds of billions of chances to do so. The Fermi paradox haunts our understanding of the galaxy. If the galaxy is old enough and large enough for life to have arisen many times, then where is everyone? This is the Fermi paradox, named for physicist Enrico Fermi, who reportedly asked the question simply, over lunch, long ago, where are they? If intelligent life evolved elsewhere in the Milky Way, why have we found no evidence of it? Perhaps life is rarer than we hope. Perhaps intelligent life rarely survives long enough to communicate. Perhaps the distances are simply too vast and the signals too faint. Perhaps we are not listening in the right way. Or perhaps the answer is something we have not yet thought of. The Fermi paradox is not a solved problem. It is an open wound in our understanding of the galaxy and our place in it. a question that keeps us humble before the silence of the stars. The galaxy will keep surprising us. Every time we build a better telescope, we discover that the Milky Way is more complex, more ancient, more structured, and more mysterious than we thought. New populations of stars are found. New streams of tidal debris are mapped. New properties of the central black hole are measured. New details of the galactic magnetic field are resolved. The galaxy is not a solved problem. It is an ongoing investigation, an object so large, so old, so intricate that even with centuries of careful observation and the most powerful instruments ever built, we are still in the early chapters of understanding it. And that, quietly, is one of the most wonderful things about it. The galaxy ensures that there is always more to learn. Always another secret waiting behind the next curtain of dust and time. And now, the stars begin to dim behind your thoughts. We have drifted through 100 more quiet truths about the galaxy we call home. From its inside-out formation to its distant future as an elliptical galaxy. From the ancient stars in its halo to the newborn suns, still igniting in its spiral arms. From the rogue planets drifting between the stars to the gravitational waves rippling through its bones. The Milky Way is not simply a backdrop. It is a living, changing, ancient and still growing structure. One that contains your past and the chemistry of your body and your future, in the stars still forming in its distant clouds. You live inside one of the most extraordinary objects in the universe, not as an observer, as a part of it. The atoms in your breath have been inside stars. The light falling on your closed eyes traces back to fusion reactions happening right now in suns scattered across the galactic disk. The silence around you tonight is not empty. It is filled with radio waves from distant pulsars, with the cosmic microwave background still glowing from the Big Bang, with the magnetic field of a galaxy turning slowly in the dark. You are resting in a spiral arm of the Milky Way, on a small, warm world, in the quiet middle of all of this, and the galaxy turns on around you, slowly, patiently, without hurry, as it has for 13 billion years, and as it will for billions more. Rest now. The galaxy has you. Good night. Additional Milky Way facts. Expansion far beyond the bright spiral arms of the Milky Way lies a vast and mysterious region known as the galactic halo. This halo surrounds the entire galaxy like a faint, invisible sphere. Unlike the disk of the galaxy, which contains most of the Milky Way's gas, dust, and young stars, the halo is sparse and ancient. It contains some of the oldest stars in the galaxy. Many of these stars formed more than 12 billion years ago, when the universe itself was still young. These ancient stars are often poor in heavy elements. Scattered throughout the halo are dense clusters of stars known as globular clusters. A globular cluster can contain hundreds of thousands of stars, packed into a relatively small region of space. The Milky Way contains more than 150 known globular clusters. Many orbit far above and below the galactic disk. At the center of the Milky Way lies a supermassive black hole called Sagittarius A star. It contains about 4 million times the mass of the Sun. The Milky Way is orbited by smaller galaxies, including the Large Magellanic Cloud and the Small Magellanic Cloud. Their interactions stretch massive streams of gas across space. Our galaxy belongs to a group of galaxies called the Local Group. The largest member besides the Milky Way is the Andromeda Galaxy, which is slowly moving toward us. In roughly 4 to 5 billion years, the Milky Way and Andromeda will merge into a single larger galaxy. Throughout the Milky Way, enormous clouds of gas collapse under gravity to form new stars. Astronomers estimate the galaxy forms about 1 to 3 new stars every year. Not all planets stay bound to stars. Some become rogue planets drifting through the darkness between stars. There may be billions of these wandering worlds in our galaxy. The Milky Way also contains neutron stars and magnetars, some of the densest and most extreme objects known. Our solar system travels around the center of the galaxy at roughly 220 kilometers per second. It takes about 230 million years to complete one orbit. Since its formation, the Sun has completed around 20 galactic orbits. The Milky Way may contain hundreds of billions of planets. Some could potentially support life. Even with modern technology, humanity has explored only a tiny fraction of this vast galaxy. When we look up and see the Milky Way across the night sky, we are seeing the inside view of a spiral galaxy more than 100,000 light-years across. It is the cosmic home of our sun, our planet, and every human who has ever lived.